Welcome to another Mathcast. In this episode we're going to be taking a look at how to calculate volumes involving cylindrical shells. Shell's method is one of the more important methods that we study that has to do with how to calculate a volume. Remember, the cross-sectional areas here are really not cross-sections at all. They're concentric cylinders that make up the volume of the figure that we're trying to figure out. In this case, we have a little bit of a different looking region. We're asked to find the volume of the figure obtained by rotating the area bounded by the curves y squared equals 3 minus x, y equal root 3, x equal to 0, and x equal to 3. So we have several different boundary conditions here that we have to take into account. First, let's talk about the x boundaries. We've got x equal to 3, which would be right there. I've also got x equal to 0, so over here. And then I have y equal to the root of 3. And I have this curve, y squared equals 3 minus x. And chances are, at some point, we're going to have to solve that in terms of a different variable. So let me go ahead and do that. Let me solve that in terms of x. If I have y squared equals 3 minus x, then that says that x is 3 minus y squared. That might come in handy a little bit later, so let's just hold on to that. Alright, so what area is it? Well, it's the area bounded by all the curves I just talked about, so it makes sense that it's the area in here that we're trying to rotate, in this case around the x-axis. So I'm taking all of that area in there and I'm going to rotate it around the x-axis. Alright, seems easy enough. Now let's remind ourselves what the pieces of Shell's method are. Shell's method says that the volume is the integral from where we start creating our shells to where we end. In this case, it would be from 0 to root 3. Remember, since I'm rotating around the x-axis, then a typical shell would come from a horizontal rectangle on the interval of integration. And so if I think of rotating that rectangle about the x-axis, then the figure that's created is a shell. And by shell I mean simply a cylinder that looks like this. But the cylinder has a depth to it. So it has an interior piece as well. So it's not just an area, it's actually a shell that's created. And the same over here. And because of that, this figure has volume, but in the limit as delta x goes to 0 is a shell, which is only what we would consider to be surface area. And so the formula for Shell's method is the surface area of a cylinder, which is 2 pi times the radius, and in class I've been calling it the shell radius, times the height, which is in this case, what I'm calling the height of the shell. So this is how we handle any shell method or cylindrical shell problem, and I'm integrating with respect to y because this particular rectangle is any y between 0 and root 3. And so that's why my integral runs from 0 to root 3 in this case. So all we have to do at this point is figure out how to express our shell radius and our shell height. Now the shell radius, as you can see, is the distance from the axis of rotation to our rectangle. So this is my radius. And it's easy to see that the radius is whatever y I choose. So this is my choice of radius. So I'm just going to write 2 pi y. And the shell height refers to the actual width, in this case, if you want to think about it that way. This is the shell height. And since I'm integrating horizontally there, shell height is nothing more than right function minus left function. Now those are in terms of x. So the rightmost function here is the line x equal to 3, and the left function is the line x equal to 3 minus y squared. So if I do right minus left, then this will end up as 3 minus y squared dy. So remember, this is nothing more than saying right minus left. We've become used to that in doing our horizontal integration. All right, if I put everything together here, let's clean this up a little bit. This becomes 2 pi y. The 3's, if you notice, are going to cancel, and it's going to leave me with a positive y squared, which that seems easy enough. So if I was asking you simply to set up the integral but not solve, you would just stop here, but this one seems easy enough to go ahead and carry out. So if I did that, I would end up with 2 pi times y4 over 4 evaluated from 0 to root 3, which turns out to be 9 pi halves. So the volume of the figure that results there is 9 pi halves. So this is a really good example of using shell method. Just make sure that you understand, in looking at this shell that we have over here, exactly what is being done in terms of the figure. When you're dealing with cylindrical shells, it's best to understand what makes up the shell radius and the shell height, and that's the two major things that you have to watch out for. Alright, we're going to take a look at one more video where we calculate volumes. In that particular video, we're going to be looking at rotating around an axis other than the x or the y axis, and so you have to be a little bit careful about how you apply some of these formulas that we've come up with so far. Thank you for watching.